Hello, everyone, and welcome. I'm Katherine Hambleton with NASA's Office of Communications. Thank you for joining us here today at Wallops Flight Facility in Virginia to talk about the science launching aboard the Cygnus spacecraft to the International Space Station. Cygnus is packed and ready to launch atop an Antares rocket during a 5-minute window that opens at 8:03 p.m. tomorrow night. We will have time for a few questions after each of our speakers today. As I bring them each up. For those on the phone, if you'll press *1 to be entered into the queue at any time. And for those following us online, please use the hashtag AskNASA. Here with me to give us an overview of the science going up for this launch is Pete Hasbrook with the Program Science Office for the International Space Station. Pete, can you give us an overview of what's on board for this launch?
Sure. Thank you, Catherine. Thank you all for being here, and a special thanks to all of you who are watching on NASA TV as well. On behalf of the speakers, we're very proud and pleased to be here. We're glad for Antares and Orbital and ATK returning to flight this week. It's a great thing for the International Space Station and for the program. The Cygnus can bring a variety of cargo to the International Space Station, and tomorrow on the Cygnus vehicle we've got over 1,000 kilograms, 1,046 kilograms of scientific cargo supporting our work on the International Space Station. That's about 2,300 pounds of cargo, or as I understand it, it's about a third of the cargo being launched tomorrow. The ISS is a laboratory in space, and it's a very versatile laboratory. Unlike laboratories that you see here on Earth that may specialize in one discipline and probably focus on one very small part of that discipline, the ISS supports a broad range of experiments on board and a broad range of research. At any one time, we've got over 100 experiments going on during the 6 months right now, Expedition 49 and 50. We've got over 300 experiments in the plan over the course of those 6 months. Our experiments range from from biology, microbiology, to earth and space sciences, human research, technology demonstration, and education and outreach, as well as physical sciences. We have to date over 2,000 different experiments that have been done across the partnership and around the world on the ISS. We have over 2,900 scientists who have been participating in research, and we've had over 95 different countries researching or doing activities with the ISS. And the research that we're doing and the outreach that we're doing are advancing our knowledge toward exploration, future exploration of other planets, as well as benefiting our life here on Earth. Now, in the speakers that you'll hear after us, I'm going to sort of preview 2 of those for you, and both of them have to do with combustion. You're going to hear about a fire that's going to be initiated on the Cygnus vehicle, but after it's finished its mission with the ISS, after it unberths. And the Cygnus, in effect, is going to become another laboratory for us. This kind of a fire we could not conduct in a human environment. So being able to test these materials and do this kind of test after Cygnus undocks gives you another idea of the benefit of the Cygnus vehicle for us. Another speaker is going to talk about a phenomenon called cool flames, where flames actually burn at a lower temperature than we're used to, a lower light level. So it's harder to see, very hard to recreate here on the ground. But in microgravity, we can study it, which will bring benefits for us in combustion engines and detecting fires. Some of the other science launching on the Cygnus tomorrow, for example, for our European partners, the European Space Agency, they're launching several experiments to support their crew member who's launching in November. Thomas Pesquet from France is part of the European Science and Astronaut Corps. Among the experiments that are launching, the aqua membrane experiment is a technology demonstration which is improved technology for purifying water through a membrane. It'll be even better than the environmental systems, the recyclable environmental systems that we have on board. There's something called AquaPad, which is able to measure the quality of water in space. There's the Everywhere application on a tablet, on let's say an iPad, to be able to take the data very easily for the astronaut. They take less time to take the data and write it down and record it and send it, which allows them to do other things. We have a couple of experiments in the physical sciences area, 2 of them studying crystals and solidification of metals. One of them with a really cool acronym, it's the Device for the Study of Critical Liquids and Crystallization, or DECLIC. It's a partnership of NASA with the French Space Agency. And it's studying alloys that act like metals, but these are clear alloys. And as they freeze or solidify, we can look at the crystals and the solidification boundary, as we call it, and apply that toward our computer models on the ground and get a better simulation and prediction of how metals solidify and what is their strength, what are the properties of the crystals. Another one is called the solidification using a baffle in sealed ampules, or SUBSA. And it's studying materials that are used in semiconductors, cooling them actually at very high temperatures. But again, improving our electronic devices and benefiting us here on Earth, as well as smaller communication and smaller transistor type of, for future spacecraft. I'd like to refer now to my first slide. Ongoing on ISS right now, we have several successes, one of which is the fluid shifts experiment. In space, our fluid would shift from our legs, where it would be on Earth, up into our torso and our head. And we believe that's contributing to some visual impairment issues that we have seen and realized now in some of our astronauts over the course of time. And so as you study the fluid shift, not only in the eyes, but in the ears, in the eardrums, and your intracranial pressure, we hope to learn more about what's causing these visual impairment issues. Very important to us as we're going on to other planets, longer missions on to Mars. You see Scott Kelly there. Scott was one of the 2 one-year crew member missions. Scott and his crewmate, Mikhail Kornienko from Russia, landed in March, but we are continuing this joint experiment. It's a joint experiment with our Russian partners. So the crew on board right now, Expedition 49, is finishing up their final measurements. And if I could have my next slide, please. We've had some great successes recently in using the ISS as a molecular and microbiological laboratory. We have the Genes in Space students experiment that's been able to replicate DNA and to identify what the DNA is. We have the Wet Lab Smart Cycler, which is also able to amplify. When you hear amplifying DNA, I'm an engineer at heart, but to me it's building up and growing enough of it that you're able to analyze it and really extract the DNA from it. And finally, the biomolecular sequencer, which is actually able to identify the microbes, identify the DNA. And what that does for us is, again, for future exploration, we want smaller equipment. We want to be able to analyze the results in situ right there without having to bring home the samples. And so these are examples of the great science we have going on ISS for us right now, bringing us benefits here to Earth and improving our exploration for our journey to Mars. And before the next speakers come up, if you want to look more about the research that we're doing, www.nasa.gov ISS-science. If you do Twitter, give us a shout out at ISS_research. And we also have an app for that on iPhones and Android, the Space Station Research Explorer. It's a really easy app to use, and it's got a lot of great information about all this. So thank you, Catherine, for the opportunity.
Thanks, Pete. Next, I'd like to welcome Dr. Jitendra Joshi, the Technology and Integration Lead for the Advanced Exploration Systems Division at NASA headquarters, to speak with us about the Spacecraft Fire Safety Demonstration Project, also known as SAFFIRE. This is the second in a series of investigations that look at to study fire inside a Cygnus after it departs the space station at the end of its mission. Dr. Joshi, why are you doing more missions?
Great question, and I will give you the answer in 5 minutes. Safety is the top priority, whether it's a human mission or a robotic mission when we launch them. Especially when it comes to human spacecraft, safety is our #1 goal. In order to have safe habitation systems, we many a times have redundancies built into the spacecraft. For life support systems, we'll have some spares or some other redundancies. There are some systems you can do that, and some systems you have to be extremely conservative so that nothing bad happens. One of the least understood risks in space is how fire propagates, starts, how do you control the fire, how do you detect the fire. All these things are something that you cannot from Earth make a call, 911, come, I have a fire here, right? You have to be proactive in building your material. As such, what we have been doing when building spacecraft is we've been extremely conservative. We've been using materials for 30 or 40 years. They are heavy, and the footprint is larger than we would like. Newer and newer materials are coming into play now. To use those materials, we have to first qualify them as safe for use in space. We have conducted experiments for fire for over 2 decades in space. Mostly, they have been the size of this particular index card. And because they were conducted with humans in the loop, you had to do them in the microgravity sciences glove box. For more than a decade ago, we were trying to say, how do we conduct large fire experiments? Because that is what matters. So can you roll the video, please? So the Cygnus, the previous Cygnus mission carried Sapphire 1, and I will show you that particular mission. So it's basically a box that goes in Sapphire. It has 2 chambers. One is the avionics chamber, and one is actually the chamber where you have this large sample, the orange-looking one. There are 6 fans that blow air through that at a certain rate. It resides in the Cygnus. It goes up there. It is not turned on while Cygnus is attached to the space station. Once Cygnus deberths from the space station, the folks at Dulles Orbital at Dulles will actually start the experiment, initiate it, and then we start the fire. The experiment goes on for 2.5 hours. All the data gets collected. Cygnus, while it is coming back to Earth, or in a systematic deburn, all the data gets transferred. So I will briefly tell you what happened during Sapphire 1. We had this particular Sibyl cloth, which is a cotton fiberglass plot. What you see there, the flame traveling, was a model we knew based on very small samples. What actually happened was the fire burnt a little bit slower when we had a convective flow going in there, a forced convective flow. It was in fact 60% less than what we had expected, the rate of growth of the flame. So that teaches us some lesson. It's not that it's growing slower. Growing slower might have other ramifications. We think those are because of the wall effects where it was contained. So the next particular mission, which is going to launch tomorrow, is Sapphire 2. It essentially has the same size of the sample, but we have 9 samples here. So there is a rationale why these samples were chosen. 4 of them are silicon samples, and they are basically samples of different thickness, okay? Because thickness affects how fire happens, how the material burns. A thicker material might burn differently than a thinner one. This is one of the most prevalent materials used, which is flammable. Then we also have something called Nomex. Nomex is a commercial material, which is a fire retardant material that is used. We are also carrying smaller sizes of the material that we used in the first one. That helps us assess scalability. Does the small material burn the same way as the big one in the same conditions? What you see in my hand here is acrylic glass. This material is used in the windows of spacecrafts. This was burnt in one gravity, Earth's atmosphere, and it did not burn fully with the time that we exposed to it. The same material, a structured or a flat glass that would be used in potential missions later on, we're going to try doing the same experiment. We're going to vary the parameters from Sapphire 1 a bit based on what we learned in terms of the slow boundary layer movement, and that is the goal. So this gives us some understanding of more materials. It will give us an understanding of how we can scale things in terms of sample volume, size, and predict flammability. It will help us make missions safe, because once you understand how this fire propagates, you can have mitigation strategies, you can have detection strategies. As more and more materials are being planned to be used, we need to do this. In order to increase reliability, we are going to also have materials that we'll take as raw materials, do in space manufacturing to fix stuff. all these things need qualification. So to build more reliable missions, to build more self-sustaining missions as we move further from low Earth orbit, Sapphire will play a long way. This was a tremendous effort on part of the ISS engineers, orbital sciences, and the advanced exploration systems in trying to smartly use, as my earlier speaker said, smartly use this returning vehicle as a lab on its own. So we want to thank all the folks who have made this possible, and we hope to get the results we are looking for.
Thank you. We will now take questions from those in the room about Sapphire, as well as those on the phone and on social media using Ask NASA. I will bring the microphone to you, and if you will state your name and your affiliation. Let's see, we'll go third row over here.
Gene McCulloch, Talking Space. How many times do you plan on flying Sapphire, and what other materials do you plan on using? Thank you.
So our current plan is to have, in this series of experiments, there is going to be one more Sapphire 3. Then we will have Sapphire 4 to 6. So let me tell you what Sapphire 3 is going to be. It's going to be the same material that was used earlier on, but we will vary some of the other parameters in order to understand the flame propagation. So that will complete that story. We have never completed the bookend of starting a fire, extinguishing a fire, detecting the products, and send when it is safe. So then we have planned Sapphire 4 through 6, in which we will actually start the fire, we will have detectors at different places, we will have combustion products monitoring. So we know in the flow of the air, that is the baseline flow, how do these products transfer? Where do they reach? Where do we have? We'll also test some scrubbing material for taking care of the combustion products. See how effective that is. We're planning to fly sensors, which are more than the state of the art, in order to detect that. So that's at least 6.
Next question, right here.
Jason Ryan with SpaceflightInsider.com. Sapphire 1 flew, and it did some studies in this before. Can you tell us what, if any, the elements from this mission are follow-ons to the original mission? Thank you.
The original, if I get your question right, sir, there were some original experiments that were done on the space station, and then Sapphire 1 was done. No, sorry.
Yeah, there's another Cygnus that did something similar.
That was Sapphire 1.
Right, correct.
Yeah.
Is there any follow-on from that mission?
Yes. So we have this material. We will have the follow-on of that. The commonality thread between Sapphire 1 and Sapphire 2 is that the whole material was, it was a 40 by 94 centimeters. Okay? Now we are going to have some medium and small size samples. So when you have that particular large sample, medium and small size samples, you actually can do a modeling in terms of whether the flyer was scalable from size of material. So that's the common thread. The other thing is, I told you there are materials of different thicknesses, which are commonly used material like silicon, or this particular acrylic glass I talked about. So that's the commonality, is the size of the materials.
Any other questions here in the room? Okay. Thank you, Dr. Joshi. Up next, I'd like to welcome Jess Robbins to speak with us about the Cool Flames investigation. This investigation, also looking at fire in space, came out of an unexpected observation in a previous experiment. Jess, can you tell us a bit about how the Cool Flames investigation came to be and how it will work?
Sure. Our project has been running microgravity droplet combustion science on the station since about 2009. And mainly looking at liquid fuels, hydrocarbons, alcohols, and mixtures thereof. And our diagnostics look at flame radiance, flame diameter, flame temperature, droplet diameter, and what we mainly see is the hot flame erupt and extinguish, and all of that evolving over time, except in certain cases with certain fuels, something interesting has happened that no one expected and has not been recreated on the ground, where this diffusion flame with the larger chain, straight chain alkanes, high carbon number alkanes like N-heptane and N-decane. What you see is the hot flame extinguishes and the droplet diameter continues to shrink at a rate far greater than evaporation alone would drive. And it took a while for the scientists to make sense of this, and the latest explanation is a low temperature chemistry event happening called a cool flame. And this experiment, CFI, is following on those experiments to follow up and attempt to better characterize what's happening with this low temperature combustion. So we can go to the next slide, and I can talk about some of the hardware that we're sending up on Cygnus tomorrow. The hardware on the left is the combustion integrated rack. That's part of the fluid combustion facility. That's where we run our combustion experiments inside the large combustion chamber in the center there. Gas bottles are loaded on the top, and we control the mixture of oxygen and diluent and pressure in the chamber, and we dispense and ignite the liquid fuel using the experimental insert on the right, which is the MDCA, the multi-user droplet combustion apparatus. And we'll see inside that a little bit later. Some of the hardware on the exterior that you can see there are the fuel reservoirs. There's two in the front. If we can go to the next slide, you'll see an astronaut replacing one of those in his left hand. And you can see the CIA inserted into the chamber, pulled out about halfway so he can access some of the hardware that he needs to replace. So a lot of the hardware is replaceable and customizable for experiments. And like I said, we've tweaked the design and used multiple different fuels over the last 7 years. And we've seen this low temperature behavior in a couple of the fuels, straight chain, high carbon number alkanes. So CFI is sending up some experimental fuels to further look into that. Normal dodecane and isododecane is an isomer with a branched geometry. And the mixture of normal alkanes with branched alkanes mimics the constituents of standard transport fuels, jet fuel, diesel, gasoline, and trying to get a better understanding of how this low temperature combustion could be implemented in development of technologies of the next generation piston engines, HCCI engines, or CCI engines. I won't spell those out for you unless anyone asks me later. So we can go to the next slide and see inside the MDCA, and this shows a droplet being dispensed between the two deployment needles between two hot wire igniters. And this is in the center of the MDCA, and there's an array of cameras in the SIR mounted to the combustion chamber, looking in and getting images of the flame, radiometric output, and a backlit view that shows the silhouette of the droplet, and so you can very accurately measure the evolution or devolution of the diameter of the droplet during the burn. And so we'll hit play here on the video, and this is a N-heptane droplet, and you'll see it's being heated by the igniters, and they'll pull away after the ignition, and you see the hot flame, and radiative extinction occurs right there, and the flame goes out. And the droplet looks pretty quiet, but wait for it. Yeah, there it goes. And so what's feeding that reignition is that cool flame, low temperature combustion, which is driving evaporation of the fuel, but not burning it as fast as it evaporates. So it creates a cloud of flammable gas, which then can reignite. And that has implications for fire safety, for long-range, long-duration human spaceflight. As you might imagine, you think the fire's out, and like one of those trick birthday candles, you walk away and burst into flame again when you're not looking or something. So that and this negative temperature coefficient region where this combustion is operating is a big component in the design of these next generation internal combustion engines as well. So for CFI on this launch, we have the hardware necessary to upgrade the facility for the CFI science, including diagnostics that don't exist right now to actually image the flame, because as you see, when the hot flame goes out, there's no visible flame. But the scientists believe that it's there, just none of our diagnostics are tuned to capture it. And so a new set of diagnostics is being set up that'll actually be able to track the hot flame and cool flame oscillations and adapt its settings so that it can follow the history of the burn. And so I think I'll leave it there.
All right. We'll now take questions from folks in the room and via online using the hashtag AskNASA. Again, folks on the line can press *1 at any time to be entered into the queue. And can we play that video one more time while I'm going to the first question, just because it's cool?
You were talking about imaging the flame as it burns. Are you just in the first generation? Were you just imaging using visual wavelengths, or were you using IR as well?
No, UV wavelengths. There's a CH filter for the hot flame that we use that does a really good job at imaging the emissions at the CH wavelength, and you can get flame diameter very clearly using the UV camera that we currently have. The next camera that we're sending up on this flight uses that same filter, but with an intensified camera that it has a deeper UV capability. And in the cool flame region, the emissions expected there are deep within that. And so there's a filter wheel that changes depending on which mode the burn is in, to capture the cool flame through a separate filter with different intensification settings on the camera.
All right. Wait. Did you raise your hand? Okay.
Jared Hayworth with We Report Space. I was wondering, could you tell us a little bit about why the experiment in particular is well suited to microgravity versus attempting to recreate the same behavior here on Earth?
Well, it's a very long, as you could see, it's about a minute long combustion event. And this, in microgravity, you get this spherical flame around the droplet. That's only because there's a lack of convection. Heavier things don't sink and lighter things don't rise because there's no gravity, or there's microgravity. And so recreating that on the ground is very difficult. We have drop towers, we have parabolic planes that can give you up to 20 seconds or so of microgravity conditions. But as you see, for the larger droplets, these tests run 2 minutes. And there's really no way to effectively characterize the entire burning history for these larger droplets, except in the station.
Gene McCulloch, Talking Space. Will you be tracking the movement of the fuels during the experiment, and if so, with what kind of instrumentation? Thanks.
Tracking the movement of the fuels? I might need a follow-up question with that. How exactly do you mean tracking the movement of the fuels?
Well, as they disperse or any way, if there's a direction of some sort that they're going in or anything along those lines.
Well, our equipment deploys the droplet in free space in a quiescent manner so that there's very little motion of the droplet. So it stays at the center, much like in the video. Occasionally, you'll get asymmetric burning or ignition that might force it an acceleration one way or the other. But those are just failed attempts that we recreate in a separate test.
And we've got one more question over here.
Hi, let's get this started. My name is Kathleen Rush. I'm an environmental broadcast journalist. I'm probably going to ask you the most difficult question in the room. What I'd like you to do is break down exactly what you've told us as if you were talking to middle school science students. Tell them why this is important and what this means for future launches.
Okay. So the efficiency of cars, the cars we all drive every day put out a lot of pollutants, some of which are greenhouse gases, and they aren't very efficient. Largely more efficient than in the past, but we believe there's a lot of work to be done to create more efficient engines, and the HCCI engine, the homogeneous charge compression ignition engines, and the reaction controlled compression ignition engines are two of the possible beneficiaries of this technology that we're investigating. If we can characterize and leverage the findings from this experiment, they can be incorporated into future technology that can possibly create cars that treat the world much better. Sure.
That was a tough question. That's all the time we have right now for Jess. Thanks, Jess. Now I'd like to welcome Dr. Liz Warren, Associate Program Scientist with the National Lab, which is managed by the Center for Advancement of Science in Space, also known as CASIS, and Henry Martin, who is the External Payloads Coordinator at NanoRacks. They're going to be telling us about some new technology going up to the station that could open up new opportunities for the National Lab and future researchers looking to conduct science experiments aboard the station. Dr. Warren, can you tell us a little bit about what's on board for the National Lab?
Absolutely. Thank you. And hello. We're excited to be here today to tell you a little bit about some of the new enabling technologies that we're launching to the International Space Station. As Catherine said, at CASIS, we are privileged to manage the National Lab portion of the International Space Station. We provide access to the space station to the research community in academia, other government agencies, and industry. We also keep an eye and look to enhance research capabilities for future investigations to the International Space Station. In the past year, the ISS National Lab has worked with implementation partners such as NanoRacks to bring new enabling technologies to the space station for the research community, including the NanoRacks external platform, Space Tango's rack space, Tango Lab 1, and the additive manufacturing facility. On this launch, I'll tell you about 2 additional research capabilities, and then Henry will tell you about some more. As Mr. Pete Hasbrook alluded to earlier, The International Space Station is an incredible research facility. You've heard just a little bit about some combustion events that are really only possible in microgravity. And that's really one of the unique aspects of the International Space Station is sustained microgravity. And for a researcher, that means that you may be provided with some unique insights that you would not be able to do or been able to find in your research on Earth. However, in some cases, the research community wants even more pristine or more pure quiescent microgravity research than is possible on a football-sized or football field-sized laboratory like the International Space Station. There's little jostles and what we call G-jitter on the space station because there's 6 people living there and a bunch of equipment on board that produces little vibrations. And so the first experiment that I'll tell you about, our first facility, if you want to roll the video, is called the Controlled Dynamics Locker. CDL is an active vibration isolation system. So what that means is it provides a very pure, pristine microgravity environment by canceling out all of the little G-jitters or little jostles that might be imparted on the rack. Eventually, this technology can be upscaled to a larger facility, but for right now, this is what it looks like. The types of research that might take advantage of the CDL include macromolecular crystal growth, plant biology, cell culture, stem cells, and also fluid physics, such as the recently announced NSF-funded fluid dynamics investigations. CDL is also programmable such that if a researcher wants to have a known vibration imparted into their experiment, they can also do that. The other facility is actually just getting an upgrade. Mr. Pete Hasbrook mentioned it earlier, SUBSA, the solidification using a baffle and sealed ampules, which is a furnace existing already on the space station. We're launching up some improvement hardware to the space station so that future users will be able to conduct, as Pete said, some semiconductor type of research to improve efficiency of semiconductors here on Earth. And with that, Henry, I'll hand it over to you.
Thank you, Liz. Good afternoon, everybody. Again, my name is Henry Martin from NanoRx. Very happy to be here. And this is also a very exciting time because just this week, the President of the United States talked about the Next Steps program where they have selected 6 companies to research the commercial habitats for low Earth orbit and beyond. And we, NanoRx, are very excited to be one of those 6, along with our friends at Orbital ATK, whom we will be launching tomorrow. So on this mission, you can see here we have 2 payloads. One is the external deployer. NanoRx is mostly known for shooting CubeSats out of the station. And this is this piece of hardware I have right here. So for those on TV, we have done that now 139 times. Oh yeah, you can hold it. This has been to space, by the way, so that's cool. Yeah, it's only 6 kilograms or something like that, 6.1. So we've done this inside the station 139 times. We are now doing this for the 2nd time on the outside of the Cygnus. So rather than it going inside of the station and the crew having to handle it, just stays on the outside of the Cygnus the whole time. And when the Cygnus unburrs, it will travel to a higher orbit than the ISS, 450 kilometers, and it will shoot out 4 lemurs from our customer. So that's our first payload. We're very excited about it, pending all nominal operations. So if you imagine the piece of hardware, it's about 6 of these things stacked up on each other, and it's about the size of your oven in your kitchen. Our next payload is the black box. So next slide, please. So here's the Cygnus. You'll see it right there. This is from OA6, the little red circle. That's it. You can go on to the next slide, too. So there it is again, red arrow, very cool shots. Crew took those, pretty neat to look at. The gold doors have a nice touch. Next slide, please. So this is, we are also excited about, is the black box. The black box is called the black box, I'll address it now, because really the outside stays the same, is power and data, but the inside you can swap out tons of different payloads. So really you just open it up, replace something, and then send it up. What's also cool about this is it's designed for near-launch payload turnover. So a lot of stuff good science, some science, cannot wait in a box for, 30 days, 3 months before it launches. It's live science. So this allows for a near-launch turnover, so we can get it up there quicker. It is also a purely autonomous operated machine. So we don't need crew interaction. Crew has a lot of stuff to do, other science to do, like combustion and thing, which hopefully we will not be doing combustion. So it really takes that element out and allows for more autonomous operation as we further utilize the U.S. National Lab through CASIS. We can handle 18 U of payloads. U is 10 by 10 by 10 centimeters, and we're really excited on this one, and we will be flying it again on SpaceX 11 in January or March, whichever that is.
All right, thanks. We'll now take questions from folks here in the room. Again, on the phone, if you press *1, and online using the hashtag AskNASA. And I believe we do have a question on the phone.
Irene Klotz with Reuters, your line is open. Irene Klotz with Reuters, your line is open.
Thank you. Can you hear me?
Yes, ma'am. Proceed with your question.
Thanks. I actually had a question a while back for
All right, we're going to go ahead with one of the questions
available?
here in the room. Let's have you here in the middle. That's going to be hard for me to get to.
Hi, I'm Arsenio from T-Minus Arduino. Quick question. How does that stabilization system of that platform work?
So this is actually plugged into the rack. So we have these.
The platform stabilizer for the quiescent thing.
Okay, my bad.
So as I understand it, it's done magnetically, and the video that you saw showed the safety capture and then the letting go. Of course, it was filmed in a one gravity environment, so that's what the little spring on top was for. But it uses magnets and lasers for alignment, I believe. But we have a fact sheet that I can send you for further detail. I think the data are that it's 500 times quieter than the International Space Station microgravity environment, which of course is fine for most research, but some people really want that quiescent. There you go. You can actually see some of the laser alignment, and it's magnetically controlled.
Next question.
Jeff Faust of Space News. For Henry, are you carrying any CubeSats for deployment to carry inside the space station for deployment?
Not on OA5. We have no internal NRCSDs, as we call them.
All right, and then for the external ones, are you doing that just to get them into a different orbit, or is that to also get around some of the congestion about using the Kibo airlock, which is in high demand?
That is a very good point. Yes, the airlock is hard to come by. So not only do we decongest the airlock traffic, this higher orbit allows for the CubeSats to stay up longer, which is everybody wants orbital lifetime. If you've got a bird up there, you want to fly it as long as you can. We are estimating that these CubeSats will be up there for 3 years versus out of the airlock anywhere from 6 months to a year. So it's really exciting for CubeSat people who want to stay in the air longer.
All right, any other questions here in the room? Again, press *1 if you are on the phone, and use the hashtag AskNASA if you are submitting questions online. All right, thank you.
Thanks.
Ed Harris is up next. He is partner at Edge of Space, and he's going to tell us about their relationship with NanoRacks and another company called Sphero as one of the payloads that is going in the black box, which you just heard about from Henry with NanoRacks. Ed, can you tell us more about your partnership and what it is that you have up here?
Absolutely. So we're flying an experiment called Spark to ISS. And what we're doing is we're flying this Sphero Spark educational robot. And I think the best thing to do before I talk about it would be to roll this really cool video that Sphero made, and it'll show you a lot about that. And I'll talk over it. The volume's not very high, so I'll talk about it while it's rolling. But as you can see, Sphero is a robotics company, and they, you may be familiar with it, because last year they came out with BB-8 Droid. It was such a big seller. I know my son got one for Christmas, along with most of his friends. And now they're all getting this one. This is the educational unit that Sphero came out with. And the experiment that we're flying to ISS actually evolved out of a partnership between Sphero, my company Edge of Space, and NanoRacks, and a series of conversations that we had about what could we do on the ISS to foster study in robotics and coding. And at the same time, a conversation we were having with NanoRacks about what could we do in the black box, the prototype black box, to test it out using the robotic arm and some other features of it. So put the two together, and over the course of the last year, developed an experiment that's going to fly. Sphero likes to talk about, sharing all of their coding. And so what we did was we created with Sphero a series of experiments. We had a series of schools that they partner with come in and develop codes using the open source app for this robot. Those codes were then loaded in the robot. It's in the black box. It will go up. It will operate autonomously, and it will be filmed. That data will then be brought back and will be used to develop a series of additional programs, lesson plans, other codes, things like that, and it will be shared open source on Sphero's website and with Sphero's partners, such as code.org. About a year ago, Sphero developed a program that they call Lightning Lab, which is an interactive community of students and teachers and makers and coders who all come together using this robot to essentially develop programming that teaches robotics and that reinforces existing curriculum in schools, teaching lower and middle school math, physics, geometry, even geography, even art, and obviously coding and computer science. To date, there have been about 75,000 programs written for this. Very few by Sphero, mostly by outside students and other coders. So what we're trying to achieve with this is to bring that constituency, that great audience that Sphero has of people who are interested in robotics, and bring that together with the idea of spaceflight and the ISS and the experiments, the educational experiments and the science experiments that go on the ISS right now, and invigorate students to study coding and robotics and STEM and STEAM by using the excitement and the engagement of spaceflight and the International Space Station. So once this is completed and the app is put out and the lesson plans are put out, things of that nature, they will immediately be available to a group of 5,000 plus schools that Sphero already partners with, 15,000 plus teachers, and over 500,000 students. That number will grow as the partnerships grow and these apps and lesson plans get pushed out. And so what we're really hoping to do is to reach eventually millions of students, all engaging in using this robot and the experiment, the excitement, the engagement of what's done on the ISS to learn coding, to develop programs, and to reinforce those lessons that they're going through right now in lower and middle schools. So it's very exciting for us, and we're looking forward to the results of this and all the great things that students come up with. Because I will tell you right now, there is nothing more powerful than an intelligent, motivated 12-year-old with a robot. So, yeah.
All right, we'll now take questions from folks here in the room as well as online. Again, press *1 to be entered into the queue, or online on the web using the hashtag AskNASA.
Jason Ryan for Spaceflight Insider. How might Sphero be used in terms of NASA's journey to Mars? Could we see this robot traveling to the Red Planet? Thank you.
Absolutely, I could see that. And I'm not doing that as a plug for Sphero. I think, the robot, there's some really interesting things that this little robot's been able to do. I mean, I've seen some of the students, for example, built a Mars rover, an actual Mars rover robot, using this as the drivetrain and essentially the computer that runs it around. I mean, that was very innovative. So could something like this, essentially commercial off-the-shelf hardware, be utilized in NASA's journey to Mars? Absolutely. How exactly? I don't know. I think we turn loose those 12-year-olds and see what they come up with.
All right. And we're going to go over here.
Gene McCulloch, Talking Space. You were saying that there are a lot of 12-year-olds motivated to doing that. do either yourself or Spiro have any plans to put this out commercially, meaning other kids outside of school could go ahead and start playing with this and maybe even posting their programs somewhere and sharing their programs online with folks? And
oh, absolutely. This is, anyone can use this. You can buy one if you'd like, right after this meeting. Or actually, I'll let you play with this one. And anyone can code for it. It doesn't have to be just a class or school children. Anyone can do it. I actually am using it right now, and I'm going to write a couple of programs. You may have seen in the video that it can be used for art classes. I happen to be an avocational artist, so I want to use it to create some art. And it can do some pretty interesting things on a canvas. But yeah, anyone can use it. It's very simple.
Go back here.
And powerful.
Hi, I'm James Robertson from the NASA Social. I was wondering what sensors were in the Spark, and if there are any plans to add, maybe extensibility or add more sensors to it.
We've talked with Sphero and Nanorax about doing another run of this eventually that would add more capability to it. We haven't gone very far with that. In terms of the sensors and what's in it right now, that's a good question for Sphero. I'm not that familiar with the engineering of it. I'd be very happy to put you in contact with them, and I know they'd be happy to answer those questions.
Arsenio with T-Minus Arduino here. Is there any possibility of the Sphero being able to be programmed with C-like languages like Arduino instead of a graphical programming interface?
Again, that's a question for the Sphero people. I'll be tempted to say yes, but don't hold me to that. I think we'll get you to the Sphero people and they can answer that question.
Secondarily, how well does it behave in zero gravity since it's offset reaction wheels?
I was waiting for that question. So I actually got that question before I came here, before I flew up here from Houston. And I got it from my son, who is a 12-year-old, who plays with the robot and Minecraft and all of this, and so he's my expert on these things. And I asked him, I said, what do you think this is going to do when it goes up, when we fly it in microgravity? And he kind of looked at it and he said, I don't know, but it'll do something cool. And so I'm not being flippant. We don't know. That's why we're going to fly it, and we're going to experiment with it. We'll manipulate it with the robot arm inside the black box. There's a metal plate that's actually somewhat magnetized that we'll be able to, at some point, have the Sphero attached to that emulates approximately the gravity on Mars. So we did that to expand the experiment. And we gave those capabilities to those factors to the various schools and said, write a program, see what you want to do. So about 6 schools across the country in 6 different states wrote programs that are integrated into the model that's flying tomorrow. And we'll see what happens. And we'll be very happy to share all the video and the data that comes back as well.
All right, thank you.
Mm-hmm.
All right, and I believe we've got a question from social media.
Yes, we have a question from one of our followers, Robert Perlman on Twitter, and he asks, is the Sphero flying commercial off the shelf, or did it need to be modified for use on the space station?
The only thing we modified, I believe, none of it was modified except the shell. I think we had to reinforce the seal on the shell, if I remember. But otherwise, it's completely off the shelf. And that was really a central part of the experiment. We didn't want to build a new robot. We wanted to take one that's already in the classroom, already being used, and fly it and see what happens. And again, imbue that experiment with the coolness and the excitement of spaceflight.
Thanks, Ed. That's all the time that we have for questions on Edge of Space and Sphero right now. Next, I'd like to bring Pete Hasbrook and Dr. Liz Warren back up. If anyone has any questions generally about the research conducted aboard the space station or the National Lab. All right.
Hi, Ken Kramer, Universe Today and Northeast Astronomy Forum. I have a question for the first speaker about visual impairment the astronauts are suffering. I wonder if you could talk a little bit more about that. Tell us about roughly how many of the astronauts are suffering visual impairment. Have we learned anything yet to mitigate those effects? And can you talk a little bit too about the progression over time? Does it stop? Does it get worse? What happens? Thank you.
I can talk a little bit about it. I'm not the physiologist able to talk a lot about it. As far as what we've seen, it was actually kind of a recent discovery to realize that astronauts were having vision impairment. As astronauts would come back from their flight, some of them would have a little worse eyesight. And frankly, the people that were working with the astronauts thought, well, who's flying? It's middle-aged people, and your eyes get bad. And so that's kind of what happens. But somebody went back and did a systematic study and realized that in the longer duration crew members, there was a little higher rate of visual impairment. And people were seeing, some of it was blurred vision, some of it was wool spots. I don't have the percentages of the short duration like a shuttle crew member versus the long duration. As far as are we able to treat it yet, when you saw the picture of the fluid shifts experiment, one of the things that they're doing is using a Russian facility. It's basically a hard lower torso, kind of like the spacesuit that we have over here, with a waist seal on it, and you can pull a little bit of a vacuum on the body. And so what they're doing is trying to pull a lower pressure on the lower legs and see if that'll pull some of the fluid out of the head. Meanwhile, they're measuring the eye pressure, the cranial pressure, the ear pressure, the cochlear pressure. So that is a possible mitigation or a possible countermeasure for it. As far as have we seen enough to know how to treat it beyond that, I would say I don't think we've been there long enough.
And do they recover?
It varies. Some get back their regular vision afterward, and some have had some vision that has remained impaired. And before you ask me who that was, that would be a medical condition that we wouldn't divulge if I knew.
All right. We've got another question coming in from online.
Yep, this one is from John Lewis, and he's asking, in relation to the lighting effects experiment, have we taken advantage of information potentially gained from submarines, and if yes, how, and if no, why not?
So the lighting experiment is a human research experiment. We're flying solid-state lights to replace our fluorescent lights on the station. These lights are controllable, so they're controllable from the light, the frequency, the wavelength of the light, as well as the intensity. So they can be dialed up and down and dialed to different frequencies. It helps with circadian shifting. You know, as you're getting toward bed, like we have outside, the light gets darker, it gets a little more red. Blue light keeps us up. As far as submarine applications, I don't know whether we've studied it there, but I can tell you that we have run a lot of studies with our flight controllers and mission control. Imagine working overnight and you're trying to shift from your normal daytime, and you've got to be alert and awake and ready to go at the emergency's notice. And so they're using lights like this under the console. So there is some comparison of the flight controllers.
All right. I know we've got a couple over here. I'm going to go over here first.
Gene McCulka with Talking Space. Are there any other student experiments that are flying up on this particular Cygnus that you might want to highlight? And is there a list available of those online? Thank you.
Geez, I don't know off the top of my head of the student experiments, but definitely we can get that list for you.
Jason Ryan, Spaceflight Insider again. This one's for Dr. Warren. President Obama's come out and he's reiterated his plans to send crews to Mars in the 2030s. Can you talk a bit about how CASES is working to maybe perhaps gear the experiments that are being conducted on the ISS towards sending crews to the Red Planet? Thank you.
Well, much of the mandate of the ISS National Lab is to benefit life back here on Earth. And much of NASA's research is really targeted toward longer duration exploration missions. So as far as I'm aware, most of our research complement is based on really Earthward facing benefits. And so off the top of my head, I'm not able to think of any exploration type of research that is happening on the ISS National Lab part.
Actually, part of the agreement between NASA and the National Lab portion of the ISS, the National Lab focuses on benefits to Earth, using the station to benefit the people on Earth, giving them access, whereas NASA keeps the exploration research. For example, all the technology demonstration that Jitendra was talking about. Also the human research, like we were just talking about with fluid shifts, immune systems. NASA keeps the lead for using the station for our journey to Mars, for the exploration. Well, for example, sending humans beyond low Earth orbit. We know that there are a lot of risks to the human body, and our human research program has a list of, 20 of them or so, from visual impairment, immune system, bone loss, cardiac, pulmonary, and what is the risk to the human, so it's characterized, and what do we know about it, and can we control it, can we mitigate it? And there's a stoplight chart of it's red until we get a certain number of subjects through this experiment. Then it's yellow because we understand what the risk is. And then once we know how we're going to treat it, is it advanced medical technology, measurement technology? Is it, screening crew members? It is extra exercise. At this point, after a certain amount of subjects in time, we can turn it toward green and maybe blue when it's totally mitigated. And that relies on how many crew members do we see coming through the pipeline in the years that we have left of station. Right now, everybody's pretty much agreed through 2024. The Europeans are doing their last ministerial meeting the end of this year. We have the capability to extend ISS 2028 and beyond, which will help us. Anything that we're forgetting right now, we'll still have a few more years of ISS to look forward to exploration.
And we've got another question that came in online.
So a question from Irene Klotz of Reuters asking, in light of the SpaceX accident, is there any cargo that you swapped out or payloads that you swapped out or added to this mission as a result of that?
I know that we did a thorough review of what was planned for the next SpaceX mission. We're waiting for SpaceX to figure out what it was and to confirm when they can launch. So I know there was some cargo that was shifted from SpaceX to OA5. Again, I don't have that list off the top of my head, but that is something that we can dig up.
And for Irene, that is also something that we can talk about in the 6 p.m. news conference as well. Are there any other questions here in the room? All right.
Nobody's going to ask the fifth grader question? Actually, can I take a shot at that one?
Sure.
So the question about, explaining to a middle school student about why would we want to research this cool flames? A thing we like to say is that research is done for different reasons. Sometimes it's to learn the benefits to benefit us on Earth. Sometimes it's to learn the physical processes to improve what you're doing. Let's say you're growing crystals, or you're solidifying metals. And so you want a better product. You want to understand how that works. And sometimes when you're doing research, you just have an aha moment. You see something that you've never seen before. And in this case, it was the cool flames. It was burning at a lower temperature, a lower visibility. And so we want to just go study that. It's what we are as humans. We want to go learn what we don't know. It's kind of that challenge. So. Oh boy.
Let me bring the mic over to you first. Or you have to hold it a little close.
What have I done?
You have to stay after school. All right, Kathleen Rush. I'm a broadcast environmental journalist. So the question I have for you, since you brought this up, there was a cover story on Scott Kelly, which went into, if you haven't read it, went into great detail about the entire study on what's being done between Scott and his brother, who is also an astronaut and remained here on Earth. You already know this. The takeaway from that was, if we could find a way that we could maintain gravity, the same gravitational force that we have here on Earth, that we then would be able to go to Mars, to send humans to other places. But until we figure out what these human bodily damages are, and if they are, shall we say, mendable, if nature will restore eye pressure, etc. So the question for the middle school science class, do you think it's possible to maintain gravity that will allow for human beings not to suffer any ailments, and how soon do you think that that's doable?
Wow. So it is physically possible to maintain gravity. If you remember the movie 2001, you have a big rotating space station. So that is still one of the things that people are assessing of when we go to Mars or go to another planet, could we launch all of that big mechanism? It's going to be very heavy if we choose to do that. But yes, you could rotate something, and they're also, I think, looking at smaller versions of what they call the centrifuge to put in some level of gravity. Maybe it's not a full 1G like we have here on Earth. Maybe it's a partial gravity. But I'm glad you mentioned the twin study as well, Mark and Scott. I did want to say that Mark and Scott, and also Mikhail and Scott, the two one-year crew members, all the data is in. We've got all the data back. The scientists are analyzing the data. And they will be publishing and announcing what they're able to announce at the Human Research Programs Investigator Workshop. It's in Galveston, Texas, in the end of January. When you're studying two people like that and what we call an N, or number of subjects of two, you really can't reveal a lot about what happened to them. But part of the reason for doing one-year mission like that was most of our baseline is with 6-month crew members. And did anything stick out that happened to Scott or Mikhail after that 6-month point? And while we may not be able to say much about that or say that that's going to happen to everybody, that is a good indicator. Hey, we need to put some more focus on that so we know more about it when we choose to go to Mars.
Thank you, Pete, and thank you, Dr. Warren. That's all the time we have now for questions. We will broadcast the pre-launch news conference. We're targeting for 6 p.m. this evening, and you'll hear more about the mission launch operations. And be sure to tune in tomorrow night for live launch coverage beginning at 7 p.m. You can visit nasa.gov/orbitalatk for more information about this launch. And you can follow along with our researchers and these studies in orbit by visiting nasa.gov/station.
Thank you all for coming.